Kamilov. Very briefly, Ulugbek is currently an assistant professor and the director of computational imaging group at Washington University in St. Louis. He obtained his BS and MS degrees in communication systems and PhD degree in electrical engineering from EPFL in 2011 and 2015. From 2015 and 2017, he was a research scientist at Merle, Cambridge, Massachusetts. He is a recipient of several awards at a very early age, I would say. So to notice NSF Career Awards in 2021, the IEEE Signal Processing Society's 2017 Best Paper Award, and he was among 55 early career researchers in the USA, selected also as a fellow for the SciLog initiative on advancing biology. He's working on several topics, but the main idea is around computational imaging, and relatively recently, learning from data and learning models, how to integrate them together with some ongoing computational frameworks in his lab. So we look forward to your talk. Ulugbek, the floor is yours. Thanks again.
Thank you, Zafer, for the nice introduction. And also thank you, everybody, for attending this talk. As Zafer said, with whom, by the way, we go a long way back. So we're both PhD students at the same time in Switzerland at EPFL. And after which we kept in touch regularly over research topics related to different aspects of signal processing and imaging. So I am assistant professor at Washington University, just as it was said. And my group here is called Computational Imaging Group. So computational imaging is this latest subset of several disciplines that includes computer vision, that includes image processing, and that includes machine learning. And my group essentially focuses on the specific type of machine learning algorithms that try to bring together information from physical models, and usually those physical models are something that represent imaging systems, and then learn models. And learn models, in my case, usually represent deep neural networks. And this is something I'm going to talk to you today. And then that framework I'm going to use to talk about these concepts is usually called Plug-and-Play Priors. So that's what all these words you see on the title. Now, it is probably not a secret, and since I'm talking at the AI seminars, that AI, or a specific statistical aspect of it called machine learning, and in particular deep learning, is really transforming imaging. Beyond imaging, it's also transforming other disciplines. But because of a lot of effort, the technology is still in its infancy. It has a lot of limitations and a lot of issues that are still continuously being addressed. And this is kind of falls into the scope of my talk. Today, I'll focus on biomedical imaging. And in biomedical imaging in particular, we've been seeing kind of a change the way we think about it. So let me give you a little bit of the way I'm thinking about the progress in the biomedical imaging at the moment. So if you think about it, originally, the imaging was really a hardware problem, right? Hardware exercise. So what does this mean? This means that you will have a point somewhere in space. You would build a device that would map this point to another point, and another point was either in the eyepiece, in a microscope, or a film, so we could print it and look at the images, right? Then we came the next stage, which I put here present, where we got computers, right? So computer I'm using on my screen here, and suddenly we could store everything digitally and use digital image processing to highlight things, to denoise things, to post-process things, and so on. So things became much more flexible. Now, we're moving to this third stage of this evolution, which is, I put there future, but it's really a near future. It's happening already now, where the information that comes out of instrument, which is usually the imaging instrument, is not used on its own. It's usually combined with some kind of learned information or learned models. Those could be neural networks or other types of machine learning models that allow you to combine information from external data sets into this image to try to retrieve hidden information, right? There are lots of images to the way it's being done. For example, if you think about face detection or classification or segmentation, in all those methods, usually there's a data set. We train a model on a data set, And by using that information, that data set concisely represented through neural network, we can do more than we could do just by a single data point that comes out from the instrument, right? So that's kind of where it falls. Now, specifically today, in that context, I want to talk about the inverse problems. And this is one of my favorite toy problems to look at because it gives me a lot of flexibility to design methods and play with different types of imaging instruments. So what is an inverse problem? So the problem we're going to look at today is trying to compute or find an unknown image X. Okay, so this is unknown image X. We would like to have it, but unfortunately, we don't have it directly. Well, instead, what we have is a measurement Y. Okay, what is a measurement Y? Measurement Y is that X that goes through some instrument, which is represented through this operator A. And of course, it's a noisy measurement, right? So then by going through A and adding a noise here, E, I obtain Y, right? So this mapping from unknown image that we want to the actual measurement that we have is usually what we call the forward problem. That's a mapping of what we want to what we actually have. Now, inverse problem is a reverse process, which is more challenging, of course, where we now try, given Y, we're trying to recover the image X. Now, the reason I call this my favorite toy problem is because many problems can be represented through the same mathematical formalism, okay? So if you think of image denoising, image deblurring, image super resolution, microscopy, CT, computerized tomography, magnetic resonance imaging, and many more, you can always represent them through this Y equals AX plus noise model, right? So here you can see different types of imaging instruments on the left-hand side. And in this column here, you see all of them can be represented as this kind of inverse problem types of formulation. And that's the reason I like it, because it allows me to abstract out all the algorithm development to the same framework and then apply it to different types of realistic problems and real applications. So let me give you two specific applications. And those applications are the ones we're going to, in particular, discuss during my talk today. The first application is a very well-known one. It's most people probably here know it. It's magnetic resonance imaging. Okay, so in magnetic resonance imaging, we don't directly acquire the image that we want. What we acquire is the K-space measurements, what is known as K-space. And in fact, K-space is a spatial Fourier transform of the image. As you see, as I get more and more K-space images and I take inverse Fourier transform, we can form the image that we actually want to have, which is the image of a nice human brain on this side, right? Now, one thing about MRI is that data collection is indirect and sequential. Okay, indirect means I don't directly get image, unlike my nice camera here, where I would take a photo and I get the image, but I get the K-space data. And it's sequential, meaning we collect sample after sample in the K-space, okay? Which basically means in MRI, longer data collection usually leads to better image quality, but it also leads to increased patient discomfort because it time to takes to scan. For example, 2 weeks ago, I got scanned in an MRI machine using 2 different sequences, and it took them nearly 1 hour of keeping me in the machine to rescan it, to get everything set up, to get everything for sure good enough quality and resolution in my scan. So it can take quite a long time to do this. And here you can see an example of MRI scans that we're going to work on. This is a liver image. It's a 4D data set, meaning there is a 3D images. I'm showing you just one slice. And then there's also time, which is not really time. It's a breathing phase. It's a free breathing scan. The person is breathing as we're scanning them. So you can see this liver is moving their 10 breathing phases. So this is if you do a full scan, if you make a 2-minute scan, which means you really accelerate image acquisition, you can see you can have a lot of artifacts. And then if you do 1-minute scan, it gets even worse, right? This is a setting, MRI setting. Let me talk to you about the second application that we can potentially talk about today, which is optical tomography, or specifically intensity diffraction tomography, okay? The reason I wanted to put in IDT here, intensity diffraction tomography, is because it has a very simple optics, okay? It's probably one of the simplest microscopy setups you can have, where you have a light source, which is LED array, so LED array, right? Each point here is a LED. You put a sample, you have objective, you have a lens, and you finally have a digital camera that collects the intensity measurements, okay? So let me show you a little bit how it looks like. If I illuminate one LED here, it will come to the sample, it goes through the lens, and finally what we observe is image that looks like this. So this is an intensity image corresponding to one LED illumination, right? But how do we get the image? Well, we're going to do tomographic setup, means now we're going to take a bunch of images by illuminating different LED positions. So by illuminating different ones, I'm going to get images at different angles, right? Because the angle of illumination changes. And by finally correcting many, many angles and many projections of this image, we can try to form a 3D image of the refractive index distribution of the sample. Okay, so what is a refractive index? The refractive index is what makes light bend. It's a quantitative metric. It usually can tell us something about the material we're looking at. So if you have a refractive index, you can look at it and also get some physical information about it. It's a complex quantity, in fact. It has both real and imaginary parts to it. Okay, so IDT is challenging because it's ill-posed, as you can imagine. It's it doesn't cover all the angles, unlike CT. You lose phase information, means you only collect intensity information, and it's data intensive because you're going to take many, many 2D images, usually hundreds of 2D images, each one of the size of your camera, to form one 3D image. Okay, so it's highly data intensive. All right. And then basically the three challenges that we would like to address within the context of in-house problems are slow acquisition, imaging artifacts, and big data. So let me kind of go over it. So the first challenge is as I told you, acquisition in many of those problems, in those problems, is too slow for some applications, right? Why is it slow? Because as I said, acquisition could be sequential and indirect, right? So you need to collect the data indirectly and sequentially to be able to form images. The second challenge, reconstructed images contain artifacts. And here I show you some examples. This is MRI, the streaking artifact. This is intensity diffraction tomography. You can see as I'm going through the slices of this sample, there's a ghosts of different slices that leak into each slice, right? This is an artifact because we don't have a good axial resolution because of the missing cone. And finally, here's an example where temporal resolution is quite slow of the image data. And finally, third is high computational memory requirements, because we're interested to do 3D imaging where it's 3D space, XYZ, 4D, it could be XYZ time, and 5D could be XYZ time and spectrum. So we can keep on going there. And as we go, the computational requirements grow. All right, so we quickly review the inverse problem setting. I gave you the challenges and I gave you two examples. Let me quickly talk about a very easy formula for a practical deep learning based imaging solution. Okay, that's training of supervised artifact removing convolutional neural network. All right, so this has been extremely successful recipe starting from maybe about 2015, 2016. It became pretty big in the context of inverse problems. So what do I mean by this? So suppose we have an imaging system, right? So you can pick MRI as an example, or optical tomography, or any other imaging system you're working on. And suppose we can do two types of scans. We can do a good scan, ideal scan. So in MRI, it could be a long scan. So they put me for 1 hour into machine. They get a very sharp image of myself, right? So they get a very high quality image. And then you do a realistic scan, or the scan you would like to do ideally. Let's say it's a fast scan in MRI, right? Then you're going to get artifact corrupted image like this, you see. So a simple recipe is to say, yeah, look, I have a good image, I have a bad image, they're matched together. So why don't I just train a neural network to remove those artifacts from the image? So how do I do it? I pass the bad image through the neural network, it comes out, and then I'm going to compare it to the reference, and I'm going to update the weights of the neural network to try to get as close as possible to the reference image here. Okay, so this is in fact, then you're going to obtain something like this. So the image you see here is the 1 minute scan data going through a CNN and giving you this image, which has been digitally post-processed using convolutional neural network, right? Yeah, so that's a very traditional pipeline. There are hundreds of papers on this topic, and it has been extremely successful in different applications. Now, if we think about it, we can start thinking, okay, let's adopt this framework, right? So what are advantages? Let's say I decide to pick this framework. I have a collaborator in some imaging system, and I want to use this approach to accelerate my image acquisition or reduce artifacts and so on. What are the advantages? And I guess I could open the floor to people in this talk to make this more interactive. Can anybody tell me what is the advantage of using this frameworks that I presented on the slide?
Maybe for practical use, faster acquisition.
Faster what? Faster acquisition. Yes, definitely. By doing this, you can definitely, because essentially you're acquiring faster, but then you're improving the quality using a neural network, right? So acquisition itself is way faster. So you're doing this digitally. Anyone else? There are many actually, I'm going to just show you 3 of mine afterwards. There are many potential benefits of using this approach compared to other machine learning approaches or other strategies or anything else.
Maybe this can naturally remove some sort of artifacts which are kind of present due to long acquisition times as well, like motion artifacts. If you
definitely
do it faster, then you will have less motion artifacts.
Definitely,
many other things as well, but yeah.
I think what you're getting to is in fact a flexibility, because you're not modeling the artifact per se, you're really giving a data. So long you can acquire 2 sets of data, good and bad, you can always deploy this, right? To try to fix this, to computationally improve this, right? Definitely. So let me give you like 3 of my answers. I mean, there are many, by the way, this list is not exhaustive at all. Okay, first, very easy to implement and deploy. So I take an existing deep learning framework, say TensorFlow, PyTorch. I take an existing neural network architecture, DNCNN, UNet. You load up in Python. There are lots of GitHubs with similar CNNs. So you just train it and you get some result, right? That are very easy to deploy. It's relatively fast at test time due to GPU, natural GPU acceleration, right? So, back in the day when I was a PhD student, it was pain to implement things on GPU. Like I didn't like CUDA. Implementing in CUDA was completely uncomfortable. So we would write our optimization algorithms mostly in MATLAB. Some advanced people would write them in Python, and really some people then would do in C++ or something who wanted to try to make things fast. But now with those neural networks, they're naturally GPU supported, right? So you just implement in PyTorch. It takes care of GPU on its own, which allows you to process things in seconds or sometimes milliseconds, depending on the dimensions of the data. And finally, no need to explicitly model anything. And as that's something that I think, Zafer was hinting at, is that it's very flexible. You don't need to know what's the statistical pattern of this, artifacts here, or is it white Gaussian noise here, or is it something else, right? You just train a neural network and hope it will learn how to remove it. It's learned automatically from data. Okay, so those are 3 potential advantages I pointed out, but there might be more. Now, this also begs the second question: what are the limitations of this approach, right? And probably all of us are aware that there is no magic bullet. So there's advantages, but they also come with some limitations. And maybe let me open again to the question to the floor. Anybody has an idea what's the advantage or limitation of this? By the way, don't be afraid to speak out. I know Zafer is not afraid because we know each other, but if anybody else would like to engage, I'm very happy when people do that.
I guess like to train that model, you need to collect 2 types of images, both the bad one and the good one, and it's a supervised one. So you need like something as ground truth.
Exactly. And from the way you're saying, I'm guessing you're already interested to looking beyond supervision. So definitely, yeah. So the framework, the way I set it up, right? I said, you get a good image, bad image, then you can do supervision. Then the question comes, can we always do supervision, right? That's a valid question. That's definitely a potential limitation. Maybe one more, anybody else can, and then I'm going to give you my 3 limitations. Anybody else can see issues with this? Especially those who actually tried it. They probably, many of us probably have tried a version of this. So we've seen the potential issues with this. All right, going chance 1 to answer, chance 2, going 3. All right. I'm guessing people are slightly scared to speak up or being very careful. So let me tell you my 3 limitations. So one big one, I don't know if anybody has tried this. It does not allow for efficient model adaptation. What do I mean? Relationship between the final algorithms that we got. What is our algorithm in this case? The algorithm are the weights of the neural network. Okay, that's our algorithm. Okay, so the relationship between our algorithm and its output are non-trivial. They're all embedded into the weights. So how do I update it, the algorithm? Let's say I get a new setting, more noise, less noise, more artifacts. Well, you have to retrain the model, right? So there's no flexibility for model adaptation. That's a one big limitation. Number 2, that's what we've already heard from Kansu, that when she said that we need a ground truth for training for supervised learning. So that limits applicability to some problems, because there are problems where supervision is just not possible. And finally, it doesn't exploit any known physical models. The advantage that it is blind to anything, right? It's not using anything we know about imaging instrument, right? So this is both advantage and in fact a limitation, because you can get a lot of information if you have information of how the data is being collected in the first place. Okay, those are 3 limitations that I could hear, but there are lots of more. So this kind of brings me to this very actively researched topic of trying to bridge those limitations. And many people have been working in this by trying to combine model-based optimizations and deep learning. And Plug-and-Play Priors framework is probably one of the first frameworks to try to do this. And I have been actively working in this area. Now, anybody who wants to get a deeper information, the information I will not be able to cover within this talk itself, feel free to take a look at the recent tutorial that I have written together with Greg Buzzard, Charlie Bauman, and Brent Wahlberg for the inventors of the plug-and-play priors approach. So there is a tutorial that goes over all kinds of aspects of using plug-and-play priors. But today I'll give you some ideas of how to think about this, this methodology. Today, although I give you 3 points of what, outline of the talk, in fact, we're going to focus on the first point only. Okay, we're going to focus on the concept of regularization by artifact removal, or RARE methodology. If we have time, we might do a brief stop at the 3rd bullet point, but we're going to definitely skip the 2nd bullet point because, but anybody who is interested, I can share the slides so you can take a look or look up at the references if you're interested in this topic. All right, let's talk about the RARE framework. So regularization by artifact removal framework is something that has been inspired by plug-and-play priors, and I'm going to explain this in a second. So it's a simple algorithmic framework to try to integrate physical information from instruments and learn information from neural networks. Okay, so let's start by talking about how we're going to integrate the learned models. Okay, the way we're going to integrate learned models into the algorithm is we're going to pre-train an artifact removing neural network. Okay, you can see a little star here in front of pre-train because we're going to discuss how to do this pre-training later. But let's suppose you've trained it already. Okay, you have a neural network that takes artifact corrupted image as an input and produces an artifact free or artifact reduced image as an output. Okay, so this neural network essentially characterizes, in some sense, a prior knowledge that can separate image desired information from undesired information, meaning the artifact patterns. Okay, and we're going to talk about how to train this very soon. Okay, this is the first model. The second model will be the physical model. Okay, so what is a physical model? It's the model that infuses information from the forward model of our inverse problem, right? So here's an example of the forward model. As I said, that we have a measurement y, we would like to recover x, right? And we know the physics of imaging instrument, which is characterized by this operator A. And I gave you examples of different types of operators for different types of imaging inverse problems, right? So the physical model is something that does an operation like this. So here you see an operation which is identity minus some constant times gradient of the data fidelity term G. Okay, so what does this operation do? This operation goes from less measurement consistent X to a more measurement consistent X, right? Because you're doing a gradient descent on a data fidelity term G, essentially trying to reduce the G. So by finding a minimum of this, you would get as close as possible to Y by optimizing over X. Okay, so that's a physical model. So how do we now combine the two together to obtain a rare algorithm? So there are two ways to combine. So the first way to combine is what I called here PNP form, is a sequential way to combine, right? So what does a sequential mean? First, I'm going to do a gradient descent step with respect to my forward model, right? My physical model, right? So I do more measurement consistent output. And then I take the ZT and I pass it through my artifact removing neural network to get my XT, right? Essentially, this ZT is trying to reduce artifacts in my intermediate iterate ZT, and I get XT. And I got to come back again and iterate on this, right? So if I wrote this out, it would look something like this. I start with X0, and I'm going to go through this to obtain XT, right? The final XT combines information both from the physical model and the learned problem, okay? By the way, again, nowhere here I'm talking about the training of a neural network. I'm assuming I have a pre-trained neural network. I'm just giving you an example how to use it, okay? How can you use that pre-trained neural network by combining it with the physical information? Now, the second one is this red form, or regularization by denoising form, which does a parallel form, right? It does a similar idea, but now I pass iterates in parallel by something like this. By the way, this should be, in fact, R, not D. This is a typo. This should be R. So you can see that we do a gradient descent with respect to G. So I have this update here. It has a gradient descent with respect to G, and it takes a residual of the neural network. What is a residual? Residual is when you have output minus the input to the neural network. Okay, so we're subtracting output of the input to the neural network from the output of neural network, and we're combining both of them by multiplying by tau, which is equivalent to rewriting it in this form by including the gamma here. So this is how you compute the iterates. This is the second form. And those are two quite widely used algorithms. The first one, this first form was introduced in 2013 as plug-and-play priors iteration. And the second was introduced in 2017 as a regularization by denoising iteration, okay? And I'm gonna talk to you about the roots of these two iterations in a second. Now, before I continue, are there any questions on this slide? This is essentially the algorithmic framework we're gonna talk about, where we're gonna iterate over operations like this, where we have neural networks and gradient terms of the data fidelity term. Okay, if there are no questions, let me quickly talk about the roots of this algorithm, okay? So the roots of the algorithm can be traced to proximal algorithms. Some of you might be familiar or not, but I'm gonna explain in a second, and plug-and-play priors, right? So let's consider the problem of image noising, okay? So I have some vector Z, which is a noisy version of X, right? So X is a true image, which is distributed according to some usually unknown distribution of images X, PX, and E is a noise that, let's assume it's a Gaussian additive white Gaussian noise, okay? So I have Z, and I would like to denoise the image. So image denoiser is an operator that I put R tau, where tau is the noise level here, right? This is a variance of my noise. So R tau takes a noisy image Z and tries to get me a less noisy image as the output, right? R tau. Okay, so AWG and denoiser specifically is a denoiser that tries to remove additive white Gaussian noise. Okay, so proximal operator is a mathematical definition. Okay, it's a mathematical operator that can be interpreted as an image denoiser, or it can also be interpreted as a map estimator. So here's a mathematical definition of a proximal operator. So it's essentially a denoiser, right? You can see it's a denoiser from here. So we try to find X, which is close to my noisy image Z. But I also add some prior information on it by adding a little regularization term here. So this is H map here. And tau controls how much information comes from this H function here. So for example, if you want to do a map estimator, your H could be negative log of your prior, right? In this case, you would be doing a maximum a posterior probability estimator. That's what the proximal operator would do. So you can see tau here controls amount of the noising being performed. If tau is 0, you're not doing anything on the image, right? It just becomes 0. If tau increases, more and more information is coming from the prior. Okay, so that's a proximal operator definition. Now, classical plug-and-play priors was a framework that tried to use proximal operators or map estimators to solve inverse problems, right? So it would try to say, oh, you know what I'm going to do is I'm going to do a gradient descent on my data fidelity term G, followed by a proximal operator, right? Which is defined here. I'm going to define a proximal operator that's applied to the ZT. And by iterating this algorithm, this is, by the way, known as a proximal gradient method, by iterating on this algorithm, you can prove that you're going to be solving a function that has G plus H mapped. So you're finding a minimizer of this type of function, which means you're performing maximum posterior probability estimation of an image, given the measurement. Okay, so that's essentially the root. You can see this algorithm is very similar to the algorithm I showed you, except instead of using a proximal operator here, which is defined like this, we're just using a neural network. We're just using a general neural network that perform artifact removal. Any questions here?
Just one point, Ulugbek, maybe you already clarified it. Does it have to be on the sample domain, or can you do this on Fourier space, like K-space as well? Because
yeah, that's a great question.
You had like 2 images like on raw data and the high quality data, but you assume that you already reconstructed the 2. But it could have been done already on the raw K-space data as well.
Yeah, so this is a great question. Whatever I'm talking now, X here denotes an image, unknown image. So I'm iterating over the unknown image. So I want to recover the unknown image. The measurements are all part of this G operation. That's a gradient term. But nothing in this method precludes it from being applied also in the measurement domain. You could, in fact, design a denoiser in the measurement domain, or design an operator in a measurement domain and also apply it. And that could lead to new methods that could be giving a different type of performance. And some work has been done in that area by a group in Boston University called Clem Carroll, if anybody is interested. But yeah, it can be done. But what I'm going to talk only about image domain estimation. Any other questions? All right. So this is kind of a historical tour about explaining where it comes from. However, if you look at it, when we do train neural networks, we're not performing a map estimation, right? So that interpretation, that the traditional interpretation based on map estimation does not really apply when we try to talk about neural networks that we train, right? The reason is very often we train neural networks to minimize the mean square error during the training, right? So one way to write it, in fact, we're training an operator by tuning its weights, by tuning theta, the weights of the neural network, that would be as close as possible to the ground truth image X, right? So this is essentially trying to do the MMSE estimation for the denoising problem, right? And that deep neural networks are essentially the empirical MMSE estimators that are trained over a set of images. So a set of natural images, set of MRI images, or a set of CT images, or any kind of other problem, right? So that's what we usually do. So the question is, what happens if I use non-map estimators in the algorithm, right? And in fact, you can still make a nice argument about it. So if I would put in a MMSE estimator into that algorithm I gave you, you would still end up minimizing some loss function, okay? That loss function, I called it HMMSE. It has a very ugly shape, so I'm not going to write it here. You can find it in the paper if anybody is interested. It's generally not convex, and it is not equivalent to negative log of the prior. Okay, so it's another function that you're trying to do, and then plug and play priors, but still the algorithm will be converging, and it will be converging to a stationary point of potentially non-convex function that has this shape. So you're still balancing the prior with data fidelity term when you're going to be minimizing that thing. And in fact, another interpretation could be, you can think of this as a map estimator for a new prior, which is exponential of negative h MMSE. Okay, so that could be another interpretation of this algorithm. All right. So let me show you this quickly on the simulation. This is I'm going to show you more real applications later. This is more just to give you the concept. This is done on a vanilla compressive sensing, which means we generate a random Gaussian measured measurements Y. The signal is Bernoulli Gaussian, additive white Gaussian noise. It's all completely synthetic. Okay, so we generate synthetic samples. But then the reason we do it is because we can actually evaluate the MMSE denoiser for those signals. We can have a closed form solution for the MMSE signal. I can compute it and I can put it as a denoiser inside the algorithm. But we can also train a neural network to do the same. So I can take a neural network, add noise, and train it to remove the noise. So you can see if you do this, the neural network behaves very close to the true MMSE estimator. Right? So here you show iterations versus the loss, iterations versus signal to noise ratio. Here as a reference, I'm using Lasso, which is L1 norm minimization. You can see it kind of does better than Lasso, but essentially the neural network, TNCNN based plug and play, follows very closely the true idealistic MMSE plug and play. Okay. However, there's still a little if there. The issue is that if I take a GAMP algorithm, which is closer to the true MMSE estimator, meaning it's an optimum estimator for this problem, there is still a gap between plug and play and the optimal idealized GAMP estimator. And you can see this gap here, which basically says PMP MMSE is suboptimal relative to GAMP. And the reason it's suboptimal is because we're really restricting our denoisers to be additive white Gaussian denoisers. Although the iterates that we generate inside the algorithm are not white Gaussian noise. Right? The artifact patterns that we have in every iteration are not white Gaussian noise, but they are assuming it's white Gaussian noise and passing through the denoiser. So this is making us pay this penalty in terms of suboptimalities that we see here. So that kind of brings up the question, can we do better, right? By not using just denoisers, by using general artifact removal operators. That's why we called it rare regularization by artifact removal, okay, instead of traditional PMP. All right, let me give you one more theoretical argument in support of this. This is more like a fixed point interpretation. So the statistical interpretation I gave you is very useful, but you can take a more generic fixed point interpretation of the algorithm. So let's look at this algorithms that I just talked about, right? I have a data fidelity term. I have a residual of my denoiser here, right? If I look at this and I consider two sets, let's consider the first set, which is a set of images where the gradient of data fidelity term is 0, right? Essentially, those are the set of images that are minimizers of my data fidelity term if it is convex, okay? And the second set, it's a set of fixed points of my artifact removing operator R, okay? Fixed points are the points where if I put X inside, I get X at the outside. It's a points that don't get modified. It's images that don't get modified by my neural network, okay? It goes as an input, it comes out as an output. So this set can be interpreted as a set of images that are artifact free according to the neural network, right? Why is it so? Because they don't get modified. So according to the neural network, it's a artifact free. It doesn't act on them, right? So if I take these two sets, essentially this algorithm, what it's trying to do is trying to balance those two sets. This is a sensor model. This is a prior model. If there is an intersection between the two sets, the rare algorithm will get a point inside the intersection, and you can prove this, right? You'll get something inside that will satisfy both physical model and the prior model. If the intersection is empty, you will be balancing these two by finding a point in between, where the distance between them will be controlled by this tau parameter. So if tau is 0, you'll be inside the sensor model consistency, right? Data consistency. If tau is increased, you're going to be infusing more and more sensor prior information into this recovery model. All right. And in fact, you can prove the following theorem. If you run that algorithm, rare algorithms that I showed you here, for a weakly convex G, and a non-expansive neural network R theta, I'm going to tell you what's non-expansive in a second, for any fixed step size like this, then you're going to converge to a 0 of G as 1 over T. So you can prove the convergence of these algorithms that I talked. And the non-expansiveness means if I take U and V as an inputs to my neural network, it has to be bounded by U minus V at the output for any UV. It's something you can in fact impose during the training of the neural network. Okay, so during the training, there is a method called spectral normalization that allows you to control the Lipschitz continuity, or this constant here, for the neural network. And by doing this, you can have this kind of nice convergence property of the algorithm. Okay, so this is basically just to give you a little bit more, less statistical, but more fixed point interpretation of the algorithm, which is also intuitive and useful for many problems. Because the problem is that we don't necessarily have a loss function for a general R theta. And that's why sometimes this interpretation is useful. So now let's talk about the performance. How can we achieve the state-of-the-art performance? Or basically, how do we train the neural network to do the best, right? I told you that if you train it to remove the noise, then the performance will be slightly suboptimal. So how can we try to maximize it? The way to do it is to use the idea called the deep equilibrium models, okay? So the idea is to train, so let's say here's an operator T theta. It's basically my rare update rule, right? This is my update rule. I take X minus gamma times G theta. And if you remember, if I come here, my G is this, it combines both my prior and my neural network. So this is my T. If I look at the fixed point of T, which means wherever my algorithm converges is a fixed point, right? This means the algorithm is not changing anymore. And let's consider MSE training loss. So MSE training loss means I want to make sure my fixed point is as close as possible to my training data. Okay, X star. So this might be my ground truth if I want to do supervised training, right? So it's the ground truth. I want to make sure that X bar is very close to X star. And the nice thing is that, in fact, what we can do is we can take an implicit gradient with respect to the weights of the neural network. And the idea has been known as deep equilibrium learning or deep equilibrium models, where I can simply compute the gradient of this potentially infinitely long neural network, right? Because I'm not truncating this at any iteration. I'm running this iteration until it converges, and I'm differentiating my loss at the point of convergence. And if you do this, and you can find more details in this paper here, if you do this, you're going to get this gradient with respect to weights of your loss. Now, if you do this, this can be evaluated pretty efficiently. By doing this, you can train this algorithm, neural network in this, the weights of this neural network. And if you would do this, in fact, you would really get state-of-the-art performance on many, many problems, in imaging inverse problems. So just to give you an example, many people have been fascinated by using generative adversarial networks as regularizers, okay? So here, the problem I'm considering here is reconstruction of celebrity faces. It's people's faces that are measured in a compressive sensing setup at 10% sampling rate. Okay, so you take only 10% of sampling rate, which is pretty heavy subsampling. And then two methods that I put here are pretty recent state-of-the-art methods for reconstructing faces by using style GAN2 neural network. So style GAN2 has been deliberately trained to generate human faces, very high quality human faces, and you can use it as a regularizer. And the images you see here are two methods that use the style GAN2. Okay. Now, if you use a white Gaussian noise as a prior, I'm going to get plug and play. I plug it inside the algorithm. And if I run it, I get this result here, right? You can see it's a little smoother compared to the image here. So you can definitely have smoothness here. But SNR-wise, it's pretty competitive. Now, if I train by doing what I just explained to you, by training at the fixed points of the neural network, I'm going to get the rare with the artifact removing prior, which will be as competitive. You can see it's as sharp and even better PSNR compared to the state-of-the-art methods for celebrity faces. And you can really verify it across different sampling rates. You can see it outperforms the GAN-based methods across different types of sampling phase. By the way, all this, you can read more details in the papers that came out last year, all the details there. You can also try to do it in MRI. So it's a simulated single coil radial MRI, 10% sampling. I'm going to give you experimental results in a second, but this is in a simulation. Here you can compare with ISTA-net, which is one of the neural networks, or classical total variation regularization algorithm. You can see, but by doing this rare method, you're going to significantly outperform both methods. You can see visual quality significantly improved. And this is at 10% sampling. You can do this across different sampling rates, and the performance is the same. All right, so let me now continue. So let me summarize where we're at, right? So I gave you kind of an equations of the rare algorithm, right? The update rules. Then I gave you a nice statistical interpretation of it when you do a wide Gaussian denoising. Then we talked about general fixed point interpretation, where we said, okay, based on the operators. And finally, here I told you that you can in fact do better by training an artifact removing prior by using implicit differentiation. Now let me talk about finally the original inspiration for the method is that in fact all this training can be done directly on subsampled and noisy data without any ground truth. Okay, in the previous equation, here I call this ground truth, but in fact, you could do all the training without any ground truth. And this is something I want to talk to you about now, right? So in the ideal world, the way we would train our artifact removing prior would be I have a noisy bad image and I have some ground truth and I would train this. Now in reality, we in fact don't have usually clean ground truth data. So we don't potentially have a training label. However, it's pretty easy in many applications to have two sets of measurements. Okay, so what do I mean? For example, if you have a k-space measurements, you can divide it into two, right? So you have 5-minute scan, you can divide it into 2.5-minute scans by subdividing the MRI samples that you collected into two subsets. Okay, if you have CT, you have 180 degrees, you could subdivide it again by 90 and 90 degrees, right? And so on. So you can easily get two sets of available data, although you might not have a clean ground truth data for reconstruction, right? So the idea originally, if you read original rare paper, our goal was to design a deep artifact removing priors by training directly on subsample data and noisy data, right? And this has been inspired by the paper from 2018 called Noise to Noise. And the idea is as follows. Imagine you have a set of artifact patterns on your images, right? So you have a training data set. You don't have any ground truths. But for each training sample, you have two images. Okay, both of them have artifact patterns, but artifact patterns are random. So different for every single image in the data set. So you never have a fully acquired data, but you have a set of random artifact patterns generated on that. So if in expectation, the artifacts have expectation 0. So if you would remove the signal from each of them and you would just average all the artifacts across the data set, if that quantity would be close to 0, then if you would directly use noisy and subsample data in the training, it would be equivalent to training using ground truth images. Okay, and the theory of it you can find in this paper, or deeper discussion you can find in this paper, but basically it tells you that you don't even need, for many problems, a fully sampled ground truth data, so long your noise patterns have a nice behavior, meaning if you average them over across the data set, they're close to 0. Okay, so let me show you this result in real experimental data, where we collected images over 5 minutes. So even the collected images that we have are have artifact patterns, so you cannot directly easily reconstruct it. So what we do is we train this method called the decolearn. So what you see on the top row is XYP, meaning I'm showing you X, Y, and different motion phases. So P is a breathing cycle. You can see things are moving for different breathing cycle. What you see in the second row is XYZ, means for one breathing cycle, I'm showing you different slices of this image, right? It's a 4D data set. Now, on the left here, I show you a 2-minute scan reconstruction using simple inverse Fourier transform, right? You can see, you can have all those artifact patterns here that complicate the visual analysis of these images. Now, what we could do is we could train a neural network that takes several motion artifact corrupted images for the same different motion phases and tries to train neural network using them by compensating also for deformations, right? Because you have 10 motion phases. Each one has a slight deformation if you look here, but the patterns are changing. Artifact patterns are changing. So deco-learn is a method that allows you to, it's called deformation compensated learning. It's our recent paper that allows you to learn move the motion corrupted images together with artifacts, right? So here you apply deco-learn on a 5-minute image, okay? So now what happens if I take a deco-learn and we train it on a 5-minute image, and if I would apply it on a 2-minute image, oops, sorry, here. If I apply it on a 2-minute image, you can see it will get you some performance. It's pretty good, but it's still not completely perfect, right? So this is a problem of model adaptation. I train it on a 5-minute data and I apply it on a 2-minute data, right? So you can see the reconstruction. So here, by the way, here you see a SNR and this is SSIM values. So higher is better for both. And then now if I take the same network and I plug into the rare algorithm, which is regularization by artifact removal algorithm, then I'm going to get this result, which you can see significantly improves imaging quality, bringing it closer to the deco-learn on 5-minute images. All right. So all I want to say is that the nice application of rare is you can train it without ground truth. It allows you to do model adaptation because you simply change the forward model when you do these things, and you can apply it on a large-scale imaging problems. All right, so this was kind of a little walkthrough of the rare algorithm, and this is where I'm going to actually stop. We don't have too much time for this. Go directly to the end. All right, let me conclude my talk. So today I basically tried to give you a little bit of insights into the family of algorithms that I call regularization by artifact removal, which is inspired by plug-and-play priors. And if you're interested, you can easily find more information about it online. But regularization by artifact removal essentially does two things. It has physical models and a learned model. So physical model is a forward model, gradient of a forward model. You try to reduce it. And the learned model is an artifact removing neural network. And you try to integrate them together into a single neural network model, okay? Now, by training that rare algorithm, you can really achieve state-of-the-art performance on different applications. And I showed you some on MRI. I showed you some on compressive sensing, vanilla compressive sensing, but you can see more in this slide. We don't have time to go over everything if I want to kind of give you more details on this. And at this moment, I think I will be very happy to take any questions, and I'll stop here.
Thank you, Ulugbek. Well, we are open for questions to our speaker right now. Maybe I can go with, okay, Bertojan.
Yeah, I have a question actually.
Sure.
I have some concern about this artifact removal because when you're collecting data, I presume some of these patients have some conditions and some others don't.
Yeah.
And does the process learn the effect of the condition? So if a patient has no condition and after you remove the artifacts, he may have condition or something like that. I mean, how do you see that?
By the way, this is a classical concern. Thank you for bringing this up, by the way. This is a very natural concern. And this concern has been, usually, by the way, when I give this talk or I talk to people, this concern comes up all the time, right? People say, oh, you know what? You have different patients. You trained on the data. What happens if you don't see something or you didn't see something in the training data?
But do you learn the condition or not, basically?
Oh, what is it? What are you learning? The question is deeper, actually, because the question is, what do you mean by condition? Because condition here is just the visual patterns on the image, right?
Yes, yes.
Right. So what are you learning? Right?
Somebody may have a blocked artery, and you may just move the blocking in the artery.
Yeah. Yeah. So here's the deal. It's impressively robust. Usually, it's very hard for you to remove arteries under reasonable sampling rates. Okay. And how do I know this? How can I be so confident by saying that it usually doesn't remove much? Okay, there are two things that go into this. Okay, let me find that slide. Here we go. So don't forget that when I use this neural network, essentially I have a data consistency term.
Mm-hmm.
So I'm always consistent with my measured data. So whatever condition you have in that measured data is there. And by controlling the tau, you're telling basically how much more information you want to infuse from the neural network. If the tau is 0, you're only using your data, which is suboptimal because data is noisy, right? By controlling the tau, you're going to infuse more and more information from your neural network, right? So do wanes disappear? Well, if the wane is inside your measurements, it won't. Okay, if the things have been measured, they won't disappear. And by the way, you can do incredible tests on this. The way we can test this is by actually doing robustness tests by finding the worst case patterns in the image that would lead to the worst case performance. And you can check for many measurements rates. It's remarkably robust. Okay. So things don't just end up disappearing from the images. So it's a deeper topic. If you really want to talk to, we can definitely follow up on this. But all I want to say is that your concern is valid, but we have been gaining more and more data and more insight into this kind of methods that by now we can say under which regimes we can be confident about their performance.
Okay.
Any other questions? Maybe I can go with one in the meantime. Thanks again, Ulugbek. So there were a lot of interesting results that we may chat later on as well. But something that that is also related to the previous question is you are using off-the-shelf, I guess, methods for artifact removal, like CNN type approaches.
Yeah.
But in that case,
everything I showed was DNCNN architecture.
DNCNN, okay, so that's trained for also for again for non-Gaussian noise patterns as well. But what I'm worried about is usually if you just focus on, let's say, good denoisers or good, let's say, denoiser networks, those are pretty much focused on, let's say, visual quality, and that's not necessarily following the same noise pattern as in medical imaging data. Like if you go into the low light regime and such, the noise profile will immediately make a sharp transition from a Gaussian to, let's say, Poisson or even mixed type. So, but just using this as a off-the-shelf tool, would this be, let's say, I don't know, removing something as an artifact, but which is not an artifact, which is again along the related question to, okay, how can you make sure that this is like stable and accurate, or is there a trade-off that you observe?
Yeah, I mean, one thing I have to say is that I mean, your question is again definitely valid question. It's a very important question. It's something that requires a good discussion among researchers, right? So, you know, we should not mix up rare type of algorithm, which is what I presented, with off-the-shelf neural networks. It is not an off-the-shelf neural network. Okay, why do I say this? It's because it has this term G. Okay, so let's say you have a Poisson noise. You know, I would just change this from a Gaussian noise, from least squares, to a log-based Poisson loss. So you can always adapt it. That's what I call model adaptation. So if you know statistical properties of your noise in your data, in the measurement noise, this method can be easily adapted to that specific thing. It's not just a black box that would be, you know, blind to the noise patterns, right? So the forward model can definitely be adapted. Okay, how about the neural network? Well, as I showed you, the neural network can also be trained on a specific data sets, right? So using especially DEQ type of training. So in fact, by combining these two, you're really having not a vanilla neural network, you're having something a little bit more, okay? So it's something a little bit more where you do take into account potentially statistical distribution of your noise, and you do take into account some kind of a prior, and you really can control the trade-off, meaning if you don't trust your prior, just turn it off, right? Just like with classical TV, you can just turn it off. If you trust it more, you can put more of it. That tau here is kind of a parameter that allows you to control the amount of prior knowledge you're infusing into your reconstruction. So this is the reason I like it. You have actually two blocks and you're really waiting to this thing. Now, of course, what this method does not save you from is that if you don't have training data at all, you do need the training data to learn R here, right? So this, if you don't have a training data and you cannot train the data, this is not useful. In that case, you want to go back to different methods that allow you to work without training data, right? But whenever you do have a training data, it just improves by bringing in extra information that you learned on your data, on the training data. I hope this answered the question, at least superficially, but I'll be happy to talk about it more.
Yeah, definitely. Any more questions from the audience? Well, if not, let's thank the speaker again. Thank you so much, Ulugbek, for this very informative presentation. And we hopefully would like to have you on campus as well soon.
Yeah, thank you everyone for attending this talk. Thank you for inviting me. I hope I did pass some of the points. I know it was fairly technical, but I think this family of methods are interesting, at least for the researchers in signal processing to do. Thank you all.
There was one request asking if it would be possible to share the slides, Ulugbek.
Definitely. Definitely.
Okay.
Should I send it to you?
Yeah, to me it would be fine, and yeah, I will just distribute it among the audience as well.
Okay, definitely. I'll share my slides.
Okay, great.
Thank you all.
Thank you.
Thank you.